Okay, so hi everyone, I'm Martin Schwartz. I'm a second year PhD student and I work with Philips CS and many others listed here. And we work on high resolution mapping of carbon and canopy height. And I basically work on France. And so today I will present you a case study in the Landes forests, which is southwest of France. And so, yeah, I will present you a canopy height map at 10-meter resolution on this area. So I will show you how we did this and how and the validation and comparison with other projects that already exist there. So the area we study is this place, which is an intensively managed forest in France. So many trees with the same age within one tree stand. It's really a playground. Actually, it's really easy to work on. It's flat. It's homogeneous. Like the trees have the same age within one forest stand, and there's only one species of tree. So when we zoom in, it looks like this, and so you have these kind of forest patch, which are very homogeneous. All the trees have the same look when inside one tree stand. And so the objective is to create canopy and biomass maps with this resolution, so 10 meter, only with remote sensing data. And we use Sentinel-1 and 2, and also JEDI, which is a lidar on the International Space Station. And we've put all of this in a deep learning model, a unit model. And the idea is that thanks to the deep learning architecture and the way we trained it, we obtain a high resolution map. And so, first we focused mainly on height. So I won't really talk about biomass here, but the idea is that if we have a really precise height map, we can then infer biomass with some techniques which are it poses a lot of questions, but the height map is a first step. It's the first step of our work here. So for those who don't know JEDI, I will quickly present how it works. It's a lidar which is on the International Space Station, so it sends infrared light on Earth like this, and the light is reflected by trees and like the leaves and branches, and then you get a waveform that looks like this. And from this waveform, you can extract some interesting parameters, and especially the height of trees. So basically here we took something called relative height 95, which corresponds, we can say it's a proxy for height here. So from this waveform, we extract the height of trees. And we have, over the region that interests us, like these height measurements everywhere. But you can see that there's a lot of space between measurements. So these are the measurements, and the color indicates the height. And there's a lot of space, and the idea is to fill these gaps at 10-meter resolution with those two satellites. So Sentinel-1, which is a radar, and Sentinel-2, a multispectral emitter. So to do so, we'll train a model with Sentinel-2 images that we take from the L2A product. And actually, the idea is that we will average, we'll do a pixel-wise median image. So this image is not a Sentinel image; it's an image composed of several other images, and we do the same for Sentinel-1. And we put this into the model, and we want the model to have an output that looks like this, at least for those pixels. So this is the training labels. So for each pixel, we have the height measured from JEDI, which is put as the value of the pixels, and we tell the model that this is what he should predict, at least for those pixels. And here he doesn't have any clue of what he should do. And so we do a deep learning training process, which is based on feeding the model with this kind of image and this kind of training labels for several steps, like a huge number of time, and then we adjust the model weights so that step by step the output will look like a canopy height model. So maybe this part is a bit complicated for people who don't know what is really deep learning. Just to give you an idea, what is a UNet? It's just a series of operations that an image will go through. So if this is the input image, so imagine this is an image, it will go through a series of operations like this, which are mainly convolutions. And after all these operations, the output is going to be another image with only one layer, which is our canopy height model. And all the training process will adjust the weight of all these operations and so make the model work. So after the training, we have the output, which looks like this. So this is a canopy height map of the forest of Les Landes in the southwest of France. And if we have a closer look, we have this kind of predictions. So here is just a Google map image to have an idea of how the forest look like. Here is the Sentinel image, Sentinel-1, and this is the prediction based on those two images. And so what we can see is that the model is really able to differentiate like the different forest stands with the different colors indicates the difference of height. So here we have the forest which is lower than this one, and this one is a bit higher than this one, etc. So we validated this map with first with cross validation. So we took some data and we set them aside, so they were not taken into account during the training phase, and then we did the predictions on those images, and we compared them to the height of Jedi, and we have a fairly good correlation. But we also did validation on external data, so on forest inventory, so data that comes directly from field measurements. So the model was not trained at all on this data. It's really completely independent data, and we still have a very good correlation between our predictions and the height data. So those two graphs are for two different forest inventories. So then we decided to compare this model. So this is only a visual comparison for the moment, but to other products that we have on the same area. So this is our model, and these are three other models. This one is also based on deep learning, Sentinel-2 and Jedi, but it's a model which is trained globally. This one is with machine learning, and it's also with Landsat. And this one is a local model, but it's trained with forest inventory, so much less true height values. What we can see basically is that our model has a cleaner look. So the border of forests are more sharp, more well defined, and also we can see that for instance, between those two forests, we can see that our model is really able to differentiate the two heights, while the other models have more difficulties to really do this difference. And this is the same here. We can see the different forest patches that are with different heights, and in other models it's a bit less clear. And so finally, I wanted to show some further work that we're working on. So we wanted to look at time series, and so we applied this model to evolution, so time series of Sentinel-2 images, so between this state and this state. And what we can see is that the prediction here, so when it's brighter, the trees are higher. We can see that through time it's brighter and brighter, and so this could be a signal of tree growth. And so maybe in further research, we could have a tree growth map, like yearly tree growth map that could be very interesting also to relate to biomass maps, because if the trees are growing, also biomass is growing. So that's all for this presentation. Thank you very much for your attention. And if you have any questions, you can put them in the chat. Thank you.